All right, so welcome to our free GRE prep hour for June 11th, 2020. We're going to talk about probability today. I want to make sure we're all on the same page as far as the basics of probability, and then we'll build in some combined probabilities. And look at what happens when it gets more complicated. A lot of the problems that we will do today will be out of our 5-pound book of practice problems. I like to share these partly because I like the book, and also because that way I can share them without the GRE getting mad at us about sharing their intellectual property. But we'll try to do a fair number of GRE-like problems, but we're also going to do some drills just to see if we have all the principles of probability down. Okay. So do we know what the basic formula is we're using when we're trying to figure out a probability problem? Do you know what we're looking for? How do I solve in general? If I said, what's a chance if I pick one of you that I pick someone who works full time? Or what's a chance that if I pick one of you, I'll pick someone from the East Coast? How would I do that just broadly in general? Division or ratio, right? Yeah, there's a basic formula we could use, which is that probability, the probability of something happening is the desired over possible. And if you think about it as the ratio of that in the population, that would be it, right? If I said, what's the chance that the, I don't know, next person who wins the Nobel Prize for Literature will be from Canada, one way I could try to get an idea would be to say, well, how many Canadians are there in the world out of the total world, right? Now, that won't really give me the probability because I don't know how many people from Canada are writing literature and, what percent of them are Nobel Prize contenders and things like that, right? So I would have to assume that the winner is going to get selected randomly. And in a lot of cases, that's not happening. Maybe someone's, got a better chance than average, right? I would assume that, if you're a famous writer, you have a better chance of winning the Nobel Prize than someone who isn't a writer at all, of course. But the idea is that when we're pulling randomly out of a sample, then we can just do that. So if I just put all your names in a hat and draw you out, the chance that the person that I choose is from New York is number of New Yorkers over total number of people. So we can call that desired over possible. So I think a lot of you will be able to do this drill I'm about to show you pretty quickly, but I just want you to check in and think about it. So take a minute or two to see how you're feeling about this. I'm going to put up the polling option, and the idea is just poll in any letter you like when you're ready to talk about these. If you're done, you feel good about them. If you're not done and don't feel good about them, whenever you're ready to talk, just pull in your favorite letter and we'll talk. But it'll probably be just a minute or two. If you're watching at home, you can pause the video and try it on your own. Okay, let's talk about these. So hopefully we're not feeling too bad about the first one. If we want to know the chance of rolling anything on a six-sided die, doesn't matter what it is, as long as it's one thing, you got a chance out of six, then your chance is simply going to be 1 out of 6, right? So with that in mind, what's my chance of not rolling that thing? The rest, right? 5, 6. Anytime you have two possibilities that are mutually exclusive and there's no other choice, then that's going to add to 1. And we can sometimes use what we call the 1 minus x trick to simplify. Just take away the chance that you don't want, and that's the chance of getting what you do want, right? Some things might not be mutually exclusive, right? So for instance, if I say the chance that I'll win the game is 1 out of 10, is the chance that I'll lose 9 out of 10? Well, what if there's a third option? What if I can tie or simply not play so I don't win or lose or something like that? Then it's not clear. But one thing that's important to remember on this kind of test is that when they describe something as this or not this, that's by definition binary, right? You know, you might have opinions about whether everyone, for instance, could be considered male or female. Not everyone identifies as male or female necessarily. But if you're not male or you're male, that would cover everything. Everyone would identify as male or they wouldn't, and that would cover everybody, right? So everyone in this room, for instance, is either a Grammy-winning recording artist or not one, right? There's only two options. Either you're a Grammy-winning recording artist or you're not one. That adds up to 100%, right? So that would give us our other 5, 6. Right? Okay, so then the chance that you were born on my birthday, assuming that I wasn't born in a leap year and neither were you, would be, the how many days a year are there, right? So there's 1 out of 365. Now for the same month, I made it approximate. Why do I have to make that approximate? There's 12 months, so the chance that we were born in the same month is approximately 1/12. Why is that approximate? Yeah, there's different number of days per month, and that'll affect the probability. If we're simply selecting a month out of a hat to be born in, right? There's 12 slips of paper and I grab a slip of paper, then it's 1 out of 12. There are 12 months. But the chance that I'm born in a specific month, even ignoring, at what time do parents most likely have kids or something like that, even ignoring that, assuming that part's random, there's still like, okay, there's more days in December than February. And then if you add in that other stuff, that makes a big difference. One thing the GRE has to do, because they can't make problems that are ridiculously hard to solve or that require research, is they have to cut out a lot of the complexities. So that they probably won't ask about being born in the same month because it does get really complicated and there are real world factors that affect it. So they'll say things like there's a die to roll with equally, probable sides, or there's little, identical chips with numbers written on them and you're pulling one out. So where it's absolutely guaranteed that it's really random. The only way they could mess with you on that at all would be on a quantitative comparison, where part of the challenge is that you don't always know the probabilities. So then if they say the chance that we were born in the same month, you might have to think, well, do I know what affects the chance that I'm born in a month? Are there, what are the factors? They're not going to do a lot of that, but there could be things where you realize, oh, I'm missing some of the information that I need. And so this has to be a D rather than say an A or a B. Okay, what's the chance that we were born on different days, that we're not born on the same day? Yeah, I suppose I should. I made that very vague, didn't I? So both answers are right. I meant same day of the week, like day Monday, Tuesday, Wednesday, Thursday. If it was just the same day, like the same birthday, then of course it's the 1 minus x of what we just said. So that's why test questions have to be written so clearly, right? Depending on what I meant, the answer is either 6 out of 7 or 364 out of 365, assuming again no leap year. So either of those would be acceptable because I wasn't clear on the GRE. And of course, they'd have to be clear. That's why those problems are always vetted very carefully. Great. Finally, then we have something like this, and this is where these bits of trickery can be very important. I don't want to sit and calculate all the different combinations of Powerball numbers I can get and how that compares to what I'd get. How do I find this probability? How do I find the chance that I don't win the Powerball, which sadly, as you can imagine, is pretty high? Yeah, so I take away 1 minus the chance of winning. I have all those possibilities that could go wrong, and I don't want to quite multiply by 10 my probability, but I want to multiply I want to say there's 10 of those chances, right? So I don't know so much that I'd say I want to multiply by 10 is that there's 10 different ways to I have 10 total chances out of there to win. So if you think of it as my chance of winning is 10 out of this, my chance of winning is this minus 10, if that makes sense, right? So I'm just taking away the 10, right? The chance of winning with one ticket is 1 out of 292 million, blah, 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 blah. So the chance with 2 is double that, triple that, et cetera, for 10. And then I'm just taking that away, right? And that's going to be much easier to figure out than trying to actually calculate. In general, when you have multiple chances of things, you can simply multiply your chance by that number if it's something that is going to happen, right? If it's something that is going to happen, right? So if I say, for instance, there are 88 people in class, and 3 will win a prize. What's your chance of a prize, right? If you're going to be drawn, you could say, well, if there were just one prize, I'd have a 1 out of 88 chance. If there's 3 prizes, I have a 3 out of 88 chance. You could do out all the complicated probability. You could say, well, first off, there's the chance that I win the first prize. And then I could add in, well, what's the chance that I don't win the first prize? Well, 87 out of 88. But now, let's say I do win the second prize. Well, okay, I'm going to multiply that by the chance that, assuming that you can't win 2 prizes, I'm going to multiply by that by the chance that I do win the second prize, and now there's 87 people left that could get one, and I'm going to do this. But notice that what this is going to do is it's going to cancel, and you're still going to get 1 out of 88. And then if you want to find the chance that you don't win the first prize and don't win the second prize, and you do win the third, again, it's all going to cancel out, and you're just going to get 1/88 for each of those. You're going to get 3 out of 88. So you can simplify your job and not do more work than needed on ones like that. Some of you may have learned the general rule that and means multiply and or means add. And in simple cases, that is often valuable to know, right? The more things that want to happen, the more I have to multiply in, which should make sense, right? If my chance of success is 1/2, then the chance of succeeding twice would be 1/4, and my chance of succeeding 3 times would be 1/8. It keeps getting smaller. Whereas if I could succeed on the first, second, or third time, I might add up, although as we'll see, there's some complexities with that. Otherwise, I might start saying that I have a 3/2 chance of success, which is impossible. So yes, my chance of winning would be 3/88, and I don't need to do all that multiplication and complicated stuff. I can simply say, hey, there's 3 desired outcomes. I win the first, I win the second, or I win the third, right? Out of the 88 possibilities, right? And so that would still work. Okay. Questions on any of this before we move on? Okay, so those are just the basic moves. And then the question is using this to narrow things down. One thing that can be really useful, I'm about to throw out a couple of questions that are on the more straightforward side, but that I'd also like you to be able to narrow down for that reason. So let me know. I'm seeing a few hand raises. Since we don't have a mic option, feel free just to type any questions you have into the chat or use the Q&A function. I can get to the questions if you have them. Okay, great. And yes, this video is all going to go up on YouTube. You can also watch all our previous videos on there too, so we have quite a few of them. So let's look at a couple actual GRE style multiple choice questions and just make sure we're cool with what we're doing. Right? And I think one thing that's really useful before we worry about pulling these in, some of these, if you're comfortable with probability, you may find that you can do these quite readily. Okay. And so we could say on the first one, for instance, I want to know the chance that the number I select is greater than the average. So if I have a bunch of consecutive numbers, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 25 to 34 or something like that, roughly what fraction would I expect to be greater than average? You'd expect it to be around a half. And we could be a little bit wrong about that, but we can't be a lot wrong. Because if they're spread out evenly, it would be really weird if most of them are above average, right? How could that even be? What if I said most Americans are above the average height for an American? Well, doesn't that contradict what an average means, right? How could we all be above average, or how could even most of us be above average? It can be tricky if we have more variation. But here we can pretty much say, no, that's not going to be the case. The other beautiful thing is whenever the GRE gives us a situation where it doesn't matter what the numbers are, it just says there's a list of 10. And apparently the answer can't change then, whether I do 1 through 10, or 20 through 29, or 54 to 63. If it did change, then we'd have to know what the numbers are. Since we don't, we can just lay out the numbers 1 through 10 and say, all right, well, what's going to happen? I don't know why I'm writing them kind of wonky, but what's the average value of this list? 5.5, right in the middle. Anytime you have an even number of terms, the median will be in the middle. And when you have consecutive terms, the median and the mean, the actual average, are the same. So half of them are above average and half of them are below. And it's a very precise thing. We don't need to do anything fancy in order to calculate that. Notice that if we had a smaller set, what if we had a list of 5 instead? Then what fraction are below average? Or sorry, above average? Two out of 5, right? Because with an odd list, the average is actually in the list. And so there's a 2/5 chance that it's above average, 2/5 chance that's below average, and a 1/5 chance that it is at the average, right? So we have to consider that. Whereas with the set of 10, you can't be at the average, right? Imagine trying to roll a die and get a 3.5. You can't do that, right? You can average to 3.5, but you can't get one. And so it's gonna be split down the middle. So even if we weren't sure about this, we could just in general say, hey, some of these answers are kind of odd. How am I going to have such a small or such a large chance of being above average? Now, let's say I didn't have this set up. Let's say I had something like work days, right? Could you imagine a situation where it says something like, Jesse earns more than her average on most days? How could I make that not crazy? How could that be possible? Yeah, I need a spread. It's totally possible, right? On some days she earns less. In fact, most people earn more than their average on most days because most of us, I hope, have some days off. So think of it this way. And it didn't matter if she had days off or if she just had lower earning days and higher earning days. It would still work either way. So if you're only worried about work days, it could still be happening. But imagine, for instance, that she makes $700 a day, right? So each day, Monday through Friday, I know we're getting into stats, but stats and probability, as you've probably seen, connect very much. In fact, some people, when they're taking stats in school, they're learning probability at the same time, right? Let's say she earns $700 a day, and on Saturday and Sunday, she doesn't work, so she makes 0. But again, you could do this just the same as if you know, for instance, on Saturday and Sunday, she still worked, but she earned $10. It doesn't have to be about days off, right? So you can see that total earnings, her average, will equal total over days worked. So that'll be 3,500 divided by 7 equals 500. So her average, not even days worked, sorry, because I just said her average for days overall. So her average per day is 500. Whereas on the days that she works, she makes 700. And of course, the days she doesn't work, she makes much less, right? And you can see that in other things like income, right? What if I told you that the average American has, you know, $230,000 and you said, really? I don't know very many people who have that much money. That's not actually true, but if it were, it could be like, well, yeah, but the really rich people, you know, Bezos and Zuckerberg and stuff, have so much that on average, we each have $230,000, even though they're not really sharing, right? So we can see things like that. Now that's the opposite case. That's where most people would be below the average, but it's the same idea. Outliers can really make a difference. So when we're trying to predict probability, if we know a lot about how regular a set is or whether there are outliers, it can make a really big difference. When we're dealing with regularity, then we can know the answer should be fairly predictable. So for instance, if I look at the next problem, where I'm trying to say, what's the probability that when I go through the first 100 numbers, I choose a multiple of 3, very roughly, don't worry about the exact answer. Some of you probably already know the exact answer, but very roughly, what should I say the answer should be? Again, I'm not saying what is the answer. What's the worst answer here, right? What's the worst answer? It's nowhere close, right? Yeah, that would be the chance that it's not a multiple of 3, roughly, right? Roughly. But so what I'm getting at is maybe a lot of you correctly identified that the answer is B, and that's true, it is. But just as important, I think, is recognizing whether that answer makes sense. And so if I know that a multiple of 3 should happen every 3 numbers, just like a Sunday happens every 7 days, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, every third number is a multiple of 3, then I should expect only about a third of the numbers to be a 3. Now it can't be exactly 1/3 because 100 can't be divided into 3. So we'd have to think about the biggest number we can reach that is a multiple of 3, and that's 99. So another way to think of that is our biggest multiple of 3 is 99. So if we have 1, 2, 3, 4, 5, 6, if it's the total threes from 3 to 99 would be 33 of those. And there's 33 out of a total of 100 numbers, then our chance is 33 out of 100. So here, most of the answers, except E, are very close to that. So the narrowing down is only going to get you rid of E. But sometimes even knowing which way to go from there can be important. Let's say you have a quant comp and you're comparing the answer to a third. You could say, well, a third is what I'd expect, but let's see, I'm starting on 1 and not getting to 3 till my third term, then do 4, 5, 6, 7, 8, 9, and then I'm ending also on a number that's not a multiple of 3. It should be a little less than a third. It should not be a little more than a third. And then I could know, okay, if it's quant comp, which way to go? Here I could say, if anything, it would be 32 or 33. It can't be C or D. So estimation is a big important part of this too. Just getting a rough idea. If I randomly pick, a North American person to win a prize, what's the chance that they're from Canada, right? Well, okay, I think between Canada, the US, and Mexico, Canada does not have a super large population, so the probability should be low. And if I do my math and figure out it's an 85% chance, so I've done something wrong. So narrowing things down is a big part of this. Okay. Let's build a little more. So when we think about combining, the next question would be to ask, what are the chances of both or neither or one, but we don't specify which one of these two outcomes happening? So if we know this chance is a half, and we know this chance is 33 out of 100, right? So what's the chance that both things happen? Let's say, first I pick a number and I want it to be greater than average. And then I pick a number from this other set and I want it to be a multiple of 3. What's the chance that both of those things happen? Yeah, I could just say and equals multiply as a general rule. We don't want to do a quarter because we're not saying I'm picking 2 numbers in the first problem and the chance that they're both greater than the average. I'm combining the 2 problems, the problem about the numbers 1 to 10 and the problem about the numbers 1 to 100. So the chance of the first answer was 1/2. The chance of the second was 33 over 100. So if you wanted, you could call this 16.5%, but you could also call this 33 over 200. And on the GRE, if it's, say, a numeric entry problem, you could enter this in, and that would be as simplified as it was going to get. And even if it wasn't as simplified as it was going to get, they let you enter it in, I can't even talk. They let you enter it in unsimplified. So if you got an answer like 50 hundredths, and you didn't happen to notice that was a half, 50 hundredths would still count. It would still be correct. Okay. So if that's the case, what's the chance that neither outcome occurs? What's the answer? What's the chance that I don't pick a number greater than the average and I don't pick a multiple of 3? Well, be careful. The fact that we have a remaining question should clue you in that it's not going to be 167 out of 200, because it's not a both or neither kind of thing, right? Like what if I'm checking to see who likes coffee and who likes tea? Well, there's several possibilities, right? You don't like either, you like both, or you just like coffee, or you just like tea. So I wouldn't want to say everyone here likes coffee and tea, or everyone here doesn't like coffee and tea, unless the question is, do you like both or not? Then, yeah, that would be an either or. That would be binary. Everyone in this group either likes both coffee and tea, or doesn't like the two together. It's not true that they like both. But that's a complicated group. If you say it's not true that I like coffee and tea, do you mean you hate both of them? You like coffee and not tea? You like tea and not coffee? It's mixing things together. It's like if I say everyone in this group is either a Democrat or not. But if you're not a Democrat, does that mean you're a Republican? You're not a member of one of those parties? You're not even an American, right? Whatever it is, there's multiple possibilities, right? It's different from saying who here's a Democrat and who here's a Republican. Right? So we have to look at what it would take to have neither of them happen. So what's the chance that I don't get a yes on the first question? Right, I need to find the chance of not number one and then multiply it by not number two. So the chance that I don't get number one is still 1/2, right? Because if there's a half chance that it does happen, there's a half chance that it doesn't happen, right? And then on the other one, careful, what's the chance that it's not a multiple of 3? There we go, 67 over 100. It's not just 33.333, it's 66.66. It's exactly 33, and then there's 67 left over. So the chance that we get neither is going to be 67 out of 200. Okay. Okay, cool. So we don't want to add those pieces. We don't want to say there's a half of this and a half of that. We can just directly multiply these two pieces. We can say the chance of not 1 is 1/2. The chance of not 2 is 67 over 100. So I multiply those together, and it's 67 out of 200. So if I have 200 total possibilities, 33 of them involve, in other words, I pick a number out of the first 10 numbers, and then I pick a number out of the next 100 numbers. That's I mean, you could say there's 1,000 ways that can go, but a lot of them will narrow down and simplify down. So we could say that out of every 200 draws, 33 of them will have both of the answers I want. Another 67 will have neither of the answers I want. So then what would that mean the chance would be that we get exactly one outcome? So how would we calculate? I'm seeing a lot of interesting answers, and they're different answers, right? But how would I calculate that? How would I know what the chance is of getting exactly one? Mario saying divide. Divide what? All right. Lee, my fellow San Diegan, you're saying yes to 1 times not 2 and no to 1 times yes to 2. So the question is asking, what is the chance that exactly one of the things happen, but I don't say which one, right? Like, let's say you and I are both up for a promotion, and we might both get it, or maybe neither of us gets it, but I'd say, what's the chance that one of us gets the promotion? Just you or just me? But it doesn't matter which one, just one of us, right? So there's a couple ways to do it. I would say the somewhat complicated way to do it would be to say, all right, well, what are I dealing with? I'm saying either yes to 1 and no to 2, or I'm saying no to 1, but yes to 2. Those would be, can we agree those are the two ways that this could happen to get exactly 1? Either I get only 1 or I get only 2, right? And the general rule of thumb, if I have totally separate events, but that are dependent in the sense that they can't both happen. In other words, I can't have yes 1, no 2, and no 1, yes 2 at the same time, right? Those are separate parts of reality. Just like I can't, if one person's selected, I can't select someone born in Canada and someone born in Mexico at the same time. That's not possible, right? So I could add these two things, but I would multiply the individual probabilities. So I'd say the chance that we get yes to 1 is 1/2. And the chance that we get no to 2, we've already determined, is 67 over 100. In fact, we just did this exact math already. This is the same probability as neither, because the chance of a yes and the chance of a no are the same for number 1. The chance for no on yes to is different, right? The chance of no on 1 is still 1/2, but the chance of yes on 2 instead of 67 is only 33. So if we put these together, we're going to have 67 over 200 plus 33 over 200. So before I proceed, just want to know if you have questions about this part. The 200 is what we now get, Madison, right? When we multiply, we get 200, but the 200 we got from multiplying the 1/2 times the 100. So the idea is the chance that I get a yes to question 1 is 1/2. The chance that I get a no to question 2 is 67 over 100. There's 67 numbers that aren't multiple of 3. I multiply them together to get this. And then the chance that I get a no on 1 is still 1/2. The chance that I get a yes on 2, as we determined, is 33 out of 100. Those become 33 out of 200. So the final answer is 33 over 200. The chance of just getting yes on 2 by itself is 33 over 100. But interestingly, what do these add up to? Oh, 1/2, right? 100 over 200 is 1/2. And so anytime something works out that cleanly, I always want to think, is there a way I could have seen it more easily? Sometimes there's not, or, or at least not that I can see. Sometimes there's just no way to do it easier. I just have to do the work and it happens to work out to a nice number. But notice there is definitely a way that I could see it here from having answered the 2 previous questions. If I want to know the chance that only one thing happens, I can simply look at the chance that one happen, that both happen, and the chance that neither happens, and take those out. Because these 3 have to add up to a total. So Aida's asking, is there a formula? There are a few formulas, so it gets complicated to say there's one formula that always works. The general toolkit we want to know is that when we want to have several things happen out of the same group, we're going to multiply those probabilities, and they get smaller and smaller. And when we have totally separate possibilities, neither of which can overlap with another, then we add them. So for instance, we could add up 10 chances to win the Powerball by saying, look, this could win, these numbers that I chose could win, there's a 1 in 200 whatever million chance of that. And then if I choose other numbers, these could win too, but they never both win at the same time. So it's a totally separate possibility. I can add one and I can keep adding those possibilities up, right? If I roll a die, the chance that I roll a 1 is 1/6. The chance that I roll a 2 is 1/6. So the chance that I roll a 1 or a 2 is 2/6, because it's 2 different things that I could add up. Whereas, for instance, there's some things that don't add if they can overlap. Like, what if I said, what's a chance that someone in this group is male? And let's say half of you are male. And then I say, what's a chance that one of you is going to take the GRE? Okay, almost everyone, maybe 99%. But now I'd be saying the chance that someone's male and taking the GRE, or that one or the other, either you're a man or you're taking the GRE, would be over 100%. That's certainly not true, because there's overlap. If most of you are taking the GRE, that's the same people who are male, and we don't add those up. The same reason that if I pick a number 3 times, I couldn't say the chance that I pick a number greater than the average is 3/2 over 100%. I can't do that because there's a lot of overlap between those scenarios. So if we think of a general formula, we could say, all right, the total chance is going to equal 1, right? The chance of all the different possibilities, and that's going to equal both plus neither plus just 1 in this case. If there were more things to do, right? Let's say instead of asking you about coffee and tea, I asked you about coffee and tea and wine and beer. Then, the chances could be represented by what's the chance that you like all 4 of those things, just 3, just 2, just 1, or none. But still, it would have to add up to 100%. Okay. How do we feel about that? It's all right. Gray, I'm not sure I follow your question about P probability of one or another minus probability of one and. So, oh, I see. You're to take out the overlap. Yes, absolutely. Alice, is there a question you could ask that I might help with? Tell me which part's bugging you the most. Because if you have a question, I'm sure you're not the only one. Someone's asking about probability distributions, and yeah, absolutely. We can see how things distribute over time, and we're going to come to that in the next slide. And the more we know, just like like I said, if I know the population distribution, if I know what percentage of people live in the US or Mexico or Canada, and I randomly select one, I know the chance that that I pick someone at random is going to be proportional to how many there are in that group. A lot of times when people tell me they're overthinking a problem, it usually means that there's some missing clarity on which type of problem we're dealing or what scenarios I'm allowed to go with, right? So I often want to think about, okay, so what is it that I know about this? What are the tools that I have? And a lot of times you do have to break it down into lots of little pieces. The hardest probability problems are really hard because, you know, if I'm asking about a lot of different things combined, maybe I have to run combinatorics to do all the possibilities or things like that. So it can get really awful. That's something you can delve into if you want, but it's going to be of limited payoff on the GRE. You're just, maybe you'll get one more question right that way, maybe not. I think what's more important is we have the general principles and we're able to narrow it down. Okay, good. All right. So let's do some other scenarios in terms of combining things. So we know the general idea is that if I want to know the chance that I get two results in a row, I multiply, right? And so we'll have that. Someone's asking about page number of the 5-pound book. I don't have the page numbers handy, but these were actually number 1 and 2. So when I'm using 5-pound book problems, I'll put their numbers. These are number 1 and 2 in the chapter on probability and combinatorics. Okay. So then, so if I roll, say, 2 dice, I roll a die and then I roll it again. I want to know what's the chance that I roll a 3 at least once. So I already know the chance that I roll a 3 twice, right? So let me ask that first, actually. What's the chance that I roll 3 both times? Right, it's careful. It's not I roll it 3 first time or I roll it the second time. It's what's the chance that I roll it both times? And so I want to multiply. 1/6 times 1/6 is 1/36. And that's that idea that and multiplies, that I need both things to happen and so it gets smaller, not larger. Think about how unlikely it would be, or unless I'm cheating, that I keep rolling the die and I keep getting 3 over and over again. I do it once. What if I said, I'm going to get a 3 and I did? You'd say, wow, he called it. But okay, his chances of doing that were 1 out of 6. And then I said, I'm going to get another 3, and I just keep getting 3. Whether I say it or not, you start to get surprised. You might want to inspect this die. Does it have other numbers on it? Am I cheating somehow? So it would get less and less likely. So you wouldn't want to see the number going up. You wouldn't want to see that it was 236 or 336 or 436 as it went up. On the contrary, it becomes shrinkingly unlikely. If I roll the die 50 times and I want to get 3s all the time, my chance of doing that is 1 over 6 to the 50th power, right? So that's a very, very small probability. Could happen, but I probably wouldn't live long enough to ever see that happen. Okay, so then how would I deal with some of these other ones, like at least once, or do not roll a 3? So I want to give you, again, about 2 minutes to engage with these on your own, and then we're going to discuss. Okay, so let's run through some of these. What do we get for the chance that I roll 3 at least once? Anytime we say at least, we mean that or more. So at least once means 1 or more. Rolling at least 3 means it equals 3 or more. So I'm saying 536, 136, 3 6, 2/3. Okay. So one thing you might want to think about is this a likely or unlikely thing? If I roll the dice twice, would you expect it more often that I'd get 3 one of those times, or I wouldn't get 3? In other words, does it seem more on the likely side or more on the unlikely side that out of 2 rolls, I get 3? Right? Think about it this: if there's 6 people at your office and 2 people get a gift, is it more or less likely that you'll be one of those 2 people? Yeah, it's slightly more likely that you won't get 3 because there's 5 other numbers. And so even with 2 tries, more often than not, 3 won't get selected. So my answer should be less than half. And so if I got an answer of less than half, of more than half or more, I should suspect that I'm wrong. Now, one way we could think about at least something, since we know that that means that or more, is to say, what's the chance of not doing that, right? How many people here are at least 21? Well, how many people are under 21? How many people are 20 or less? So it might help us to answer the second question first. What's the chance that I do not roll a 3? What's the chance that I don't roll a 3 at all? And remember that we're rolling twice. So we want to say the chance of not getting a 3 on the first time is going to be 5 out of 6. And it's the same the second time, right? The first roll does not affect the second roll at all, right? It's not like I pulled a name out of a hat and left it out. So I've got 5 out of 6. So the chance that I do not roll a 3 is 25 over 36. So in that case, what happens the rest of the time? The other 11/36 of the time, what's going to happen? Yeah, I roll 1 or 2 3s. So believe it or not, this chance is kind of a strange one. People were not telling me this. It's 11 out of 36. It's an odd answer. It's not super obvious. Notice that it's about a third. And that kind of makes sense. If you think about 2 chances to get a 3, and there's a chance of 1 out of 6, it sounds like it should be about a third. The problem is that it's not exactly, because if I get a 3 on the first one and a 3 on the second one, it doesn't help me, right? And I'm not cutting out. If I couldn't get a 3 the second time, then it would be exactly the third, right? If I couldn't reselect a number, if like once you rolled a 5, then that's taken off, then it would be exactly a third, right? We can definitely break it down. So we could say, what's the chance of, one way to think of it is, what's the chance of 3 on first roll? Then it's going to be 1 out of 36. Sorry, 1 out of 6. And we don't care whether you get it on the second roll. If you get it on the first roll, you're done, right? And we're not worried about if you get it again. And then what's a chance of no 3 on first, but then 3 on second? So what's a chance that when I roll the die, I don't get a 3? We already know that. Well, just on the one die, 5 out of 6. And then what's the chance that I do get it on the second roll? 1 out of 6. So notice this is 5 out of 36. So if we try to put those together, 1/6 plus 5/36 equals 6/36 plus 5/36 equals 11/36. So that's how you could break it down into pieces. But as much as possible, I'm trying to avoid doing that. This is a time test. It's ugly. There's a lot going on. I don't want to do work I don't have to. So if I can use the 1 minus x trick to make my life easier, I can just say that, right? Just like if I said, hey, how many of you have at least one kid? Well, instead of counting up how many of you have 1 kid, 2 kids, 3 kids, 4 kids, does any of you have 10 kids, right? I could just say, how many of you don't have a kid? Okay, you 5. All right, the rest of you have kids. Great, that's it. So how many chances to not get a 3? 25 out of 36. Then all in all, the other 11, we do get a 3 at least once. Renee, the reason I don't factor in that I got the 3 on both rolls is I don't care if I do, because the idea is just getting 3 at least once. So if you look at the second time on this part here, the chance that I get a 3 on the first roll, I could say the chance that I get a 3 on the first and on the second, but I'd also just as much need to look at the chance that I get a 3 on the first and not on the second, because that would still count as getting a 3 either way. And so I don't need to count that separately, so I'd stop. I could do it out. I could say all my possibilities would be yes 3, yes 3, yes 3, no 3, no 3, yes 3, and I could find 3 things, but that's even more work. That would be 136 plus 536 plus 536. And it is important to recognize that it's just as likely that I'll get it on the first try as on the second try. So out of the 36 different possibilities, 5 of them will involve me getting it only on the first try, and 5 of them will involve me only getting it on the second try, and 1 of them will involve me getting them on both tries, but that adds up to 11. That's right. Madison, yeah, we're multiplying on the second one because all of these are about rolling the die twice. And that's one way the GRE will get you. We'll be in the middle of something else and we'll forget some constraint. Oh, they said to do it twice. They said to square it. They said to convert from centimeters to meters. So I don't apologize for being mean there, right? They will get us with that. And that's the ones where I just, get so frustrated when I miss them. Can't believe I left that out. Why don't we factor getting in no 3 on the second? Because if we get no 3 on the first and no 3 on the second, then that's not one of our desired possibilities. That doesn't work. If I get 3 on the first, then it doesn't matter if I get 3 on the second, because I've already gotten at least 1 3 and it counts, right? It's like if I said, how many of you have enough points to pass the class? And you need 60 points. If you got 60 points already, then don't look at your next test. You already have enough. Right? You already have enough. I don't care if you failed the next test, if you got 100%, you already have enough to pass. That's all I was counting right now. Okay. So we're adding 1 6 and 536 because the 136 is a chance that I get it on the first roll, whether I get it on the second roll or not. And the 536 is a chance that I don't get it on the first roll, but I get it on the second. It's like my second chance, if that makes sense, right? It's a chance that I wasn't selected here, but I did get it there. It's like, what's a chance that I get that promotion? Well, I might have gotten it on Monday, and then there was another round of promotions on Tuesday. So if I didn't get one on Monday, there's also the chance that I got it on Tuesday, right? So I'm putting those pieces together. Okay. Now dealing with the at least part, what's the chance that each roll is at least 3? So when I say at least 3, that means 3 or more. So what's the chance when I roll once that it's at least 3? Just once. Just once, yeah, 4 out of 6. I'm asking for a 3, 4, 5, or 6. So each time, my chance is 4 out of 6. So if I wanted to do it all the way out, I could call this 1636, but I might make my life a little easier by recognizing that 4/6 is 2/3 and getting 4/9 as my answer. The other answer would simplify down, but 4/9 is a nice easy way to do it. Again, if you're doing a fill-in, the GRE doesn't care. 16, 36, same thing, doesn't matter. But you get 4/9. And the idea that it should be that it keeps getting smaller, right? If each roll has to be at least 3, then the more rolls I have, the less likely that gets. Even for something really likely, right? What's the chance that I don't know, survive until next week? Well, hopefully it's very high, right? My chance of not surviving on any given day is really low. So let's say there's a 99.999% chance that I survive each day. I hope there's at least that, right? I keep multiplying it along and it gets tinier and tinier and tinier. I'll probably still be able to see you next week, but it shrinks a little bit. And so anything, no matter how unlikely, it builds up over time. It's, becomes, farther and farther above 0 that something does happen, and farther below 1 that, that we get what we expect. Okay. What's the chance that when I roll 2 dice, they add up to 2, that the sum of the 2 rolls is 2? It's important to recognize that there's only one way to do that, right? I would need 1 and 1. The only way to get 1 and 1 is to roll exactly what I want each time. So anytime you're looking to roll dice or flip coins or whatever and call each shot, then you just say, what's the one chance that I'm looking for out of the total? Okay, if I roll 2 dice, there's 36 different combinations I can get, and only one of them is allowed. So that's going to be 1/6 times 1/6. Now, an intuitive answer to the last question might be, well, it's the same. What's the chance that I can call the number? It's 1/36. And if I were rolling, say, a 36-sided die, that would be true, right? The chance of a 2 versus an 8 versus a 20 or whatever doesn't make any difference. But the trick is that there's more than one way to get 8, whereas there's not more than one way to get 2, which is why if you've ever played like dice games, craps or something like that, you'll know that, you know, a 7, for instance, is much more common than a 2. There's multiple combinations that will get there. It's a bit of a bell curve, and it's exactly distributed. One of you was talking earlier about probability distributions, and you can see that this will be peaking right in the middle. The most common result is 7. And if you think about that, you can see that no matter what you roll on the dice, on the first one, you can get a 7, right? So if I roll a 1, I can get a 6. If I roll a 2, I can get a 5. If I roll a 3, I can get a 4. There's all these combinations. So that's the most likely thing. The next most likely is an 8 or a 6, because there's there's things I can roll that would immediately stop me. If I roll a 1 on my first die, I just can't get 8. Right? I can't do it. Whereas if I roll 2, 3, 4, 5, 6, I can. So that's one way to see that there's 5 ways to get 8. Right, there's 5 things I can roll on my first shot that would get me 8. So we have to think of it this way. I could get 1 and nothing. I get 2 and 6, 3 and 5, 4 and 4, 5 and 3, or 6 and 2. That's 5 out of my total 36 possibilities. My chance is 5 out of 36. And trying to do that is going to be easier than trying to look at all the things I could roll and what would happen. Right? But another way I could do this is I could say, what's the chance that my first roll allows 8? No, I didn't notice. I did not write 6, 2 twice. I wrote 2, 6 and 6, 2. Rolling 2 first and rolling 6 first are not the same thing. Those are 2 different possibilities, right? So the chance that my first roll allows 8 is 5 out of 6. All I want is not 1. Just like there might be certain performances I might have in, say, a game where I just can't catch up, right? Or if I miss too many questions on the first section of my GRE, maybe I just can't get a certain score, right? If I run too slow at the beginning of a marathon, there's no way I can average it out to, you know, a 6-minute mile. I was too slow, right? So here I can't have a 1 to get all the way to what I want. And then what's the chance that I get the matching number I need, right? So in other words, whatever I roll on the first die, there's only one number that's going to add to that to make 8. So what's the chance that I get that number? 1/6. You multiply those together. 5/6 times 1/6 is 5/36, right? So you multiply those together and you get 5/36. And this is a valuable thing that you can use in a lot of situations. You could say either, what's the chance that I get something workable, and then what's the chance that I get its pair, or what's the chance that I get anything at all, and then what's the chance that I get something that matches it. And if that sounds very strange, let me just show you briefly what I'm talking about. So for instance, let me clear this for a moment. So if I roll 2 dice again, I'll keep that 2 dice thing going since we're working with it simple. If I roll 2 dice again, what is the chance that my 2 rolls are the same? What's the chance of that? 1/6, and we might just sort of feel intuitively that that makes sense, right? But it could also say, right, what's a chance of anything at all on my first roll? This sounds really dumb, but bear with me. The chance of anything at all happening is 1, right? Something will happen. And then what's the chance of the match? There's only a 1/6 chance that it'll match. So you can apply that to things like I pull 2 cards from a deck, right? And so that's 52 cards, 13 types, right? 13 values, right? So, if you don't play cards, there's ace, 2, 3, 4, 5, 6, 7, 8, 9, and then jack, queen, king, right? So there's 13 different values you can get, 4 of each, right? So then I could say, all right, that's why they tend to stick to dice. So they don't have to teach people this if they don't know it. It's not fair if you don't play cards, right? So I could say, what's the chance that I have a pair now? Again, you can say there's nothing I can get that'll prevent a pair. If there were, say, only 1 queen, then when I pulled a queen, I'm out of luck. I just don't get a pair, right? But if everything has 3 matches, I can just say, all right, the chance of anything at all is just 1. Now, what's the chance? You think carefully, don't be too fast. What's the chance of a match? So let's say I pulled out one of the queens. How many matches are there left? How many cards are there that could be the queen, that are queens still? 3, but not out of 4. There's a lot of cards, right? There's 4 queens. I've taken one of them. There's 3 queens. How many cards are left? Yeah, 51 cards. I had 52 cards. I pulled out 1. So the chance that I get 2 of anything, 2 queens, 2 3s, 2 9s, 2 jacks, whatever, is 3 out of 51. The chance of unmatched pair, of course, is the rest. And it gets really hard really fast, right, to do this. But I could do this directly too. I could say, again, the chance of pulling something is 100%. And then now that I pulled out something, how many cards are left? 51 cards. How many of those don't match by something? 48. It's 48 over 51. And then if I pulled a third one and I wanted to match the others, it would be 2 out of 50. If they were matched. If I pulled the third card out and I didn't want it to match either, I'd have to say now, let's say I have a queen, there's 3 of those left, and there's a king, there's 3 of those left. I have to take 6 out of my total, right? But they're probably not going to do that. So in terms of simplification, the idea is that if they're asking you for a fill-in, they don't care if you simplify. If it's multiple choice, they will definitely simplify. So 3 out of 51 is a bad answer in terms of multiple choice. You'd want to recognize, as Brandon's saying, that it's 1 out of 17. But if we're doing fill-in, then there's no issue. Do we need to show? There's no such thing as showing work on the GRE. You either get it right or you don't. They don't know how you got it. They don't care how you got it. Either you have your answer or you don't have your answer, and that's it. So these are some possibilities of what you can expect, and you can play with a lot of this in your 5-pound book. But I hope this gives you a feel for some of the things you can do. Let me see if we can use this trick one more time. So I'm going to throw you a bonus question here. I'm just going to type this up really quick because it wasn't one of the ones I had ready. So I'm going to prep this here. So imagine that there's 10 couples at an event. So that's 20 people. 2 people are selected to win prizes. What I want to know is, what is the chance that the winners are a couple with each other, in other words, right? So everyone at the event, it's 20 people, and everyone at the event is part of a couple, right? There's 10 pairs of people. But 2 people win. What's a chance that, say, the 2 people who win happen to be, married or dating, right? How would we find that? So try this out. Chat it in when you have it. It's, not multiple choice. Just chat it and answer when you have it. Careful not to put 1/10. 1/10 with the chance that if I pick a couple, that my couple is the one they pick, right? So if my wife and I are at some couples event and there's 9 other couples, the chance that if if a couple is selected, we're that couple is 1 out of 10. This is a little less likely than that, because here, for my wife and I to be selected, first one of us needs to be selected and then the other one. So it's more of a coincidence. Well, I won and then you won, right? So the chance we can predict is going to be less than 1/10. It's going to be more unlikely than that. So one way we could think about it is to go in there and look at individual pieces. So I could say, you know, what's the chance of me being selected, right? So the chance that I get selected on the first poll is just 1 out of 20. There's 20 people. The chance that I get selected is 1 out of 20. And then I could say, all right, then what's a chance of my wife getting selected after that? So let's say I've been selected and now I want my wife to get selected, right? And notice we don't have to assume anything about gender here because we're just saying couples, right? So it doesn't say anything. The GRE has actually gotten pretty hip. They don't even assume anything about gender anymore. They're you know, trying to be cool there, right? So they're not going to have you assume that everyone there is male or female, or the couples that consist of male and female. And this problem doesn't either. It just says couples. So the chance that my wife gets selected is then 1 out of 19. There's 1 prize left and 19 people. So the chance that we get that this exact thing gets selected is 1 out of 380. But that's a very specific outcome we're finding. We're finding the chance that I get selected and then my wife gets selected. Now, the chance that we win is actually slightly higher than that, because as we saw with 2-6 and 6-2, it could have gone the other way, right? But we could also have my wife first and then me, which that also equals 1 out of 380. Everyone cool with that? Like, it could be the chance of me, but then it could also be the chance of her. And so that's 2 possibilities out of 380. So that gives us, so the chance of us is equal to 2 out of 380 is 190. And of course, that's a chance for any other couple. We're not special, right? Order matters in the sense of if we're listing out ways it could go, the chance that I win in particular being 1 out of 20 is contingent on it being me that we're concerned about, right? If we just said, what's the chance that one of us wins? Then we'd say, okay, that's 2 out of 20. And then what's a chance that the other of us wins? That's 1 out of 19, and it would give us the same result. So that might have been a better way to do that, right? We could have just said the chance of one of us is 2 out of 20. And then now, let's say we had that chance of the other, 2 out of 20 is 1 out of 19. That would give us 2 out of 388, or 1 out of 190. We're not adding chance of me and chance of my wife. We're adding 2 different outcomes. It could be me first then her, or her first then me. That's why we're adding those. So the idea is, you know, chance of us equals me plus me her plus her me, right? Either of these would work. So it's, and to say what's the chance that it both happens, and then or for I get it and her, or she gets it then me. Right. So JB, I'll come back to that question. It's really interesting. Yeah, and that's another thing we'll come back to. So this is one way to do it. It's not necessarily the best. Oh, I put 1 over 90. Sorry, 1 over 190. Sorry about that. 1 over 190. So, but that's just a chance that my wife and I get selected, right? We would absolutely want to multiply it by 10 to find the chance that anyone gets selected, right? We could say, okay, so the chance of any one couple is 190, right? But there are 10 couples, so multiply that by 10. Our answer is 1/19. So there's, just like the chance of getting any one combination of dice that would get 8 is 1 out of 36. I could get 2 and 8, 2 and 6 is 1 out of 36, 3 and 5 is 1 out of 36, etc. there's 5 of those different commas that'll work, so that's 5 out of 36. So an easier way to do this problem, and if you want, I can bring this work back in a moment if anyone has questions about it, but an easier way to do this problem, instead of saying what's the chance of me and then the chance of my wife, we can do what I was doing a moment ago and say, what's the chance of anyone at all? Now, again, that seems funny to a lot of people, but what's the chance of just someone? Well, okay, 1. It doesn't matter who gets selected because there's everyone there qualifies, right? Everyone there is married. If some of the people weren't married or weren't in a relationship, whatever, then we would leave them out. But everyone is part of a couple. And then we say, what's the chance that that person's spouse gets selected? So now this could be, anyone could be me, anyone could be my wife, anyone could be you or your partner, right? It doesn't matter. So we just say the chance that their spouse is selected, well, there's 19 people left, and the chance is 1 in 19, and that makes my job so much easier, right? Rather than having to do a bunch of combinatorics to determine how many different combinations of people I could get and then divide the 10 eligible couples by the total of 190 different combinations we can get, or rather than figure out me and my wife or whatever, Gary and Helen, or anything like that, I just say, what's a chance that once we pick someone, we multiply by the chance that we get the match. So Shobhakar, I don't know quite what you mean by the principle. I don't know if you mean a named principle. To me, the idea is simply that when we have a probability where any initial state would work, then we could just say, what's the chance of matching that state? If I can roll any number I want, then what's the chance of matching that state? If I have a situation where not every case would work, right? So now imagine I say there's 30 people, right? 10 singles and 10 couples. Then I could say, well, what's a chance of a married person? And again, when I say this, I'm not saying of any individual one, right? So Taylor's saying, wouldn't the chance of anyone be 1 out of 20? When I say the chance of anyone, I mean just the chance. That's why I say it sounds silly. The chance that I pick a person at all. Well, 100%. In other words, it doesn't matter who I pick. And it might make clear when I contrast it right now. So what's a chance that I pick a married person out of 10 singles and 10 couples, right? Well, then that's 20 out of 30, or 2/3. In other words, the chance that I pick someone who's married, if 10 of the people aren't married, is 2/3. It doesn't say this particular married person, just any married person. And then what's the chance of that person's spouse? And so I'd say, okay, well, let's see. There's 29 people left, and we chose 1 married person. They only have 1 spouse. It's 1 out of 29. So we'd actually get an answer of 2/3, 2/3 times 1/29. Right? So we'd get 2/87. Okay, so I hope that helps us with the chance of anyone part. What I'm getting is, in any probability problem where you know how many ways you can combine with something, like how likely it is that your initial result will work, you can use that to make things a little easier. If it doesn't matter what your initial result is, what's a chance that you and your best friend both get picked for the team, right? That's one thing. It has to be you or your best friend. But if it's a chance just that, what are the chance that, I don't know, I pick 2 people who are, say, the same gender, right? I could say, again, well, GRE probably won't do gender, but I could say, all right, what's the chance that I pick a person? And then what fraction of the people match that person's gender, right? And as long as there's at least 1 match for everybody, then that's a valid problem. Okay, so anytime I'm setting up a problem like this, I can say, what's my initial chance of getting just a workable option, a married person? And then what's a chance of getting that particular match, right? If I want to know what my chances are of winning the lottery and I know one of my numbers, I could say, well, is that number in the list, right? So let's say I chose 5 and 5 isn't one of the Powerball numbers. Well, then I lose, I'm done, right? Whereas if I know that 5 is one of the Powerball numbers, I could say now, okay, what's the chance that I also chose the next one and the next one and the next one, like that? Okay, So I hope that helped. If that was a little out there, this is not something you're as likely to have on the GRE. I hope that some of the underlying principles about using desired over possible, narrow it down, estimating, help you to approach probability a little more comfortably on this test. Anything else you have in mind specific for me? Feel free to stick around and ask. And then definitely feel free to also check out any of our course offerings if you are interested in taking a full course. Thanks, everyone. Hope you enjoyed, and good luck with your test, whether it is tomorrow or far away. Good luck to everybody.